Hello. In this problem, we have three concentric metal spherical shells. The radii are given, and the charges are Q1, Q2, and Q3. And we are asked to find the ratio of these charges given that the surface charge densities on the outer surface of the shells are equal. Okay, so here we are looking at metal shells. So we need to understand one very important thing here. So inside, okay, at any point inside metal, the electric field must be zero. Okay, so this is important here. So one of the properties of isolated metals is at any point inside the metal. Okay, so at any point inside the metal, the electric field must be zero. Okay, electric field is zero. And then we can also use Gauss law here to understand where exactly the charge resides. Okay, so here the problem says the surface charge densities on the outer surfaces of the shells are equal. Okay, so I'm not going to indicate the radius. I think radius we understand here. Let's look. Okay, so what is important to realize here is the charge distribution. Okay, so if I take any point, let's say inside the innermost shell, the electric field must be, electric flux must be zero. Okay, if the electric flux is zero, what am I saying? Okay, well, let's back it up a little. So if you take any point, okay, so let's say if you take any point in that innermost shell, so you can imagine that, so you have a shell, imagining a circle inside that metal, so that represents a sphere. At any point on that red whatever sphere or circle, the electric field is zero. Okay, so through that sphere, the electric flux is zero. So whatever charge that you place on the innermost shell should only reside on the outer surface. Okay, it cannot reside on the inner surface. So we can say Q1 resides on the outer surface. Now, because of induction, the inner surface, okay, so the inner surface of the middle shell should get an equal and opposite charge to this Q1. Okay, so that is one thing that you can say. So the inner surface of middle shell should get minus Q1. Okay, now there's another way that you can think about it. Again, if you imagine a sphere which is inside the material of that inner or the middle shell, okay, so you're imagining a sphere, Gaussian sphere, which is inside the middle shell. At any point on that sphere, the electric field is zero, so the flux is zero. So within that red sphere drawn in that middle shell, the net charge should be zero. Okay, so because net charge should be zero, you already have Q1 on the outer surface of the innermost shell. So the inner shell of the the inner surface of the middle shell should have minus Q1. Okay, I hope I'm making sense. So you have placed Q2 charge on the middle shell. It is isolated, so the total charge should stay as Q2. So on the outer surface of the middle shell, the charge must be now Q1 plus Q2. Okay, now if you understand this logic, then you can say the same thing about the outer shell. Okay, so if you imagine, let's say, imagine a Gaussian sphere within the metal of that outer sphere. Okay, at any point, okay, so this red line should be within the metal. So at any point on that Gaussian sphere, the electric field is zero, the flux through that sphere should be zero. So that means the net charge within the outer sphere should also be zero. So the inner surface of the outer shell should get negative of Q1 plus Q2. So that means the outer surface of the outer shell should have now Q1 plus Q2 plus Q3, because the total charge must be only Q3, right? So I hope you understand the distribution here. So what is the distribution here? We are only interested in outer surfaces of the shells. Okay, for the innermost shell, outer surface is Q1, the middle shell outer surface is Q1 plus Q2, and the outer shell's outer surface has Q1 plus Q2 plus Q3. Okay, so now if you take these charges and then use them to calculate the charge densities, they are equal. That's what the problem is saying. So let's write that down. Okay, so we are saying Q1 by its surface area, that will give us the surface charge density. What is the surface area of the innermost shell? That is 4 pi r square, and then that is equal to Q1 plus Q2 by 4 pi. Okay, so the radius is 2r whole square, and then that is equal to Q1 plus Q2 plus Q3 divided by 4 pi 3r whole square. Okay, now let us consider only the first two terms. Okay, so here if I look at the denominator of the second term, I have 4 pi r square into 4. Okay, so that 4 pi r square I can cancel. So if I consider only the first two terms, I can write Q1 is equal to Q1 plus Q2 by 4. Okay, so on either side in the denominator, I can ignore that 4 pi r square. So what do we have here? 4Q1 is Q1 plus Q2. So from here I can say Q2 is 3Q1. Okay, so we have expressed Q2 in terms of Q1, and now I can do the same thing. Let's say I will try to use the first term and the last term. Okay, so let's do these two. Again, I have 4 pi r square here in the denominator. Here I have 4 pi r square into 9, so 3 square. So if I use the first and the last term, I can write Q1 as Q1 plus Q2 plus Q3 by 9. So 9Q1. Again, the algebra is up to you. Okay, so you can do whatever is convenient to you. So Q1 plus Q2. What is Q2? 3Q1. Okay, so plus Q3. So from here you see that Q3 is 9 minus 4, so 5Q1. So what is the ratio here? So Q1 is to Q2. Q2 is 3Q1 and Q3 is 5Q1. So that is 1 is to 3 is to 5. So the answer should be B.